All right, so me going over. I guess what is this, part two? Yeah, this is part two of learning C++. I'm just going over. I think I'm gonna go from point three to point five. So we're just gonna have an introduction, go over some history, I guess. What is object oriented programming? What is C++? The philosophy, and yeah. Let's just get into it. Before C++, there was C. The C language was developed in 1972 by Dennis Ritchie at Bell Telephone Laboratories, primarily as a systems programming language, a language to write operating systems with, just like writing like OSs and the kernels for operating systems and shit like that. Ritchie's primary goals were to produce a minimalistic language that was easy to compile, allowed efficient access to memory, produce efficient code, and was self-contained, not rely on other programs. For a high-level language, C was designed to give the programmer a lot of control while allowing developers to write a program that could run on different platforms. C ended up being so efficient and flexible that in 1973, Ritchie and Ken Thompson rewrote most of the Unix operating system using C. I think our operating system right now is actually written in C. Is the Windows kernel written in C? And and on all three, i.e. Windows, Mac, Linux, many of the most important user line applications are written in either C or C++. Usually, yeah, let's try DB2. Get a concise answer. Yes, the Windows kernel is primarily written in C with some portions written in C++. It's the same language. The low-level nature of C makes it ideal for operating systems. So yeah, so the Windows system is still written in C, even though C was written in 1972. So, which is just crazy. It's fucking 2024. 50 years ago. That's nuts. Anyways, um many previous operating systems had to be written in assembly, unlike assembly, which produces programs that can only run on specific CPUs. C has excellent portability, allowing Unix to be easily recompiled on many different types of computers and speeding its up adoption. C and Unix had their fortunes tied together, and C's popularity was in part tied to the success of Unix as an operating system. In 1978, Brian Kernighan and Dennis Ritchie published a book called The C Programming Language. This book, which was commonly known as KNR, after the author's last names, provided an informal specification for the language and became a de facto standard when maximum portability was needed. Programmers would stick to the recommendations in KNR because most compilers at the time were implemented to KNR standards. In 1983, the American National Standards Institute, ANSI, formed a committee to establish a formal standard for C. In 1989, committees committees take forever to do anything. But they finished and released the C89 standard, more commonly known as ANSI C. In 90, yeah, we'll hear about ANSI a lot more in the future. C in 1990, the International Organization for Standardization (ISO) adopted ANSI C with a few minor modifications. This version of C became known as C90. Compilers eventually became ANSI C90 compliant, and programs desiring maximum portability were coded to this standard. In 1990, the ISO committee released a new version of C and formally named C99. C99 adopted many features which had already made their way into compilers as extensions or had been implemented in C++. C++, pronounced C++, was developed by Bjarne Schroutstrup, I don't know if I'm saying that right, at Bell Labs as an extension to C. Starting in 1979, C++ adds many new features to the C language and is perhaps the best thought of as a superset of C. Though this is not strictly true, as C99 introduced a few features that do not exist in C++. C++'s most notable innovation oversees that it supports object-oriented programming. As for what an object is and how it differs from traditional programming methods, well, we'll cover that in later chapters. C++ was standardized in 1998 by the ISO committee. This means the ISO Standards Committee approved a document called a standards document that provides a formal description of the C++ language. The goal of standardization is to help ensure that C++ code behaves consistently across different compilers and platforms. A minor update to the language was published in 2003 and formally named C++03. And the way you check your version of C++ on Visual Studio is you just go here, C++ language standard, and you can see they're talking about so ISO C++ 14 standard. You can use the 20. This is the base standard that everybody's using. You can also use ISO C++ 20 standard, which is the one I usually use. But I mean, you can, doesn't really matter. Standardized in 1990. The Global Standardization helped ensure that, yeah. Minor update to the language was published in 2003. 5 major updates to the C++ language, informally named C++11, C++14, C++17, C++20, +23 have been made since then, each adding additional functionality. C++11 is particularly added a huge number of capabilities, and will considered to be the new baseline version. Future upgrades to the language are expected every 3 years or so. Because the official name of the approved standards is complex, C++20's former name is ISO IEC. You don't really need to know that. Standards are conventionally referred to by informal names, which include the last 2 digits of the year publication. Expected publication, for example, is C++20 refers to the version. Yeah, you're always going to use this. No one's ever going to say ISO IEC 1488 to 2020. If somebody said that shit to me, I would have no idea what they're talking about. First, the version of the language published in 2020. C and C++ is philosophy. The underlying design philosophy of C and C++ can be summed up as trust the programmer, which is both wonderful and dangerous. C++ is designed to allow the programmer a high degree of freedom to do what they want. However, this also means the language often won't stop you from doing things that don't make sense, because it will assume you're doing so for some reason it doesn't understand. There are quite a few pitfalls that new programmers would likely to fall into if caught unaware. So one of the primary reasons why knowing what you shouldn't do in C++ or C is almost as important as knowing what you should do. What is C++ good at? C++ excels in situations where high performance and precise control of memory and other resources is needed. Here are a few types of applications that C++ would excel in. Video games, which basically all high and intensity video games are all coded in C++. Real-time systems, transportation, manufacturing, etc., high-performance financial applications, graphical applications and simulations, productivity, office applications, embedded software, audio and video processing, artificial intelligence, and neural networks. C++ also has a large number of high-quality third-party libraries available, which can shorten development times significantly. Isn't C++ dying? Nope. Surveys consistently indicate that C++ is the second or third most popular compiled language, behind Java and sometimes C#, and just ahead of C, and the 5th or 6th most popular language overall, excluding HTML, SQL, and shell scripting languages. C++ is one of the most popular languages for learning to code, owing to the abundance of teaching resources, a large community, and the number of college courses that teach it. With language updates every 3 years, a huge number of useful third-party libraries, and dominance in the ever-popular video game industry, C++ continues to thrive. Do I need to know C before I do this tutorials? Nope, it's perfectly fine to start with C++, and we'll teach you everything you need to know, including pitfalls to avoid along the way. Once you know C++, it should be pretty easy to learn standard C. If you ever have the need these days, C is mostly used for niche use cases, code that runs on embedded devices, when you need to interact with other languages that can only interface with C, etc. For most other cases, C++ is recommended. Trouble understanding what I mean by portability. Portability, when it comes to C and when it's being compiled and it says it's portable, is that instead of coding in assembly, which is what they're using before, C allows it to be run on any operating system, because when you run C, it's already compiled. So if I made an exe file, right? Remember when we were looking at the chapter before in the last video, it's talking about how when you compile it, it turns into machine code and then it turns into an exe, and the exe, when you run it, it loads it into your memory and your hardware runs it for you, right? So it's like, you can take this exe file that I created from in here. If I go to debug, you can take this, you can put on any operating system that has a that runs machine code or runs .exe files. It can run an executable, and you can run this, right? So that's what it means by portability. With assembly, because there's different architectures, so there's x86 and x64, and ARM and a bunch of other different architectures, they can only run on their specific architecture. Okay, so if I was writing an assembly language, it would be for that specific architecture. So you can't run this is an assembly x86. You want to be able to run it on a computer that was ARM X fucking whatever the fuck, right? Or what was it on Power Force, or what it's called? I don't know. Yeah, that's basically what it means by portability. So introduction to C++ development. Before we can write and execute our first C++ program, we need to understand in more detail how C++ programs get developed. Here's a graphic outlining a simplistic approach. So step one, define the problem to solve. So it's like brainstorming. So you're like, oh, this is the problem I want to solve. This is what I'm gonna do. Then you design the solution, write a program that implements the solution, compile the program, link the object files, test program. So this is compiling, linking, and then we're testing it. And then testing it means we're also going to debug it and go back to compiling. So define the problem that you would like to solve. This is what step where you figure out what problem you're intending to solve, come up with an initial idea for you with like it's a program can be easiest step or the hardest. Conceptually, it is the simplest. All you need is an idea that can be well defined and you're ready for the next step. Here are a few examples. I want to write a program that will allow me to enter many numbers and calculates the average. I want to write a number that generates a second maze and lets the user, or not second, sorry, a 2D maze. Let's use to navigate through it. The user wins at the reach the end. I want to write a program that reads in a file of stock prices. It predicts whether the stock will go up or down. Okay, step two, determine how you're going to solve the problem. This is the how step, where you determine how you're going to solve the problem you came up with in step one. It is also the step that is most neglected in software development. The crux of the issue is that there are many ways to solve a problem. However, some of the solutions are good and some of them are bad. Too often a programmer will get an idea, sit down, and immediately start coding a solution. This often generates a solution that falls into the bad category. Typically, good solutions have the following characteristics. They are straightforward, not overly complicated or confusing. They are well documented, especially around any assumptions being made or limitations. See, that I think that's kind of what I need to work on, is making like well documented code. Like I need to make sure when I'm writing code, because I put a comment. So comments are when you put 2/ in C++, and you can type whatever you want. So I could type like constructor for entity, right? Because this is a constructor. And then I could do the comment right here, be like, what does display do? Display is the function to display the name of the helper entity, right? But yeah, just like things like that. Being well documented is a good practice that everybody should put in their code, especially if they're going to be making it open source and let people look at it. And also if like your team, if you're working in a group or something. They are built modularly, so parts can be reused or changed later without impacting other parts of the program. That's talking about, actually, no, I'm not going to get into that. It's too early for that. They can recover gracefully or give useful error messages when something unexpected happens. When you sit down and start coding right away, you're typically thinking, I want to do something, so you implement the solution that gets you there the fastest. This can lead to programs. This can lead to programs that are fragile, hard to change or extend later, or have lots of bugs. A bug is any kind of programming error that prevents the program from operating correctly. As an aside, the term bug was first used by, okay, I'm not going to worry about, I mean, whatever. Okay, fine, I'll read it. The term bug was first used by Thomas Edison back in the 1870s. However, the term was popularized in the 1940s. Engineers found an actual moth stuck in the hardware of another computer, causing a short circuit. Both the logbook in which the error was reported and the moth are now part of the Smithsonian Museum of American History. It can be viewed here. Let's go and view this out. Okay, there's the moth in the logbook. Great. Alright, various studies have shown that on complex software systems, only 10 to 40% of a programmer's time is actually spent writing the initial program. There's 60 to 90% is spent on maintenance, which consists of debugging, removing bugs, updates to cope with changes in the environment. For example, to run on a new OS version, enhancements, minor changes to improve usability or capability, or internal improvements to increase reliability or maintainability. Consequently, it's worth your time to spend a little extra time. It's worth your time to spend a little extra time up front before you start coding. Think about the best way to tackle a problem, what assumptions you are making, and how you might plan for the future in order to save yourself a lot of time and trouble down the road. We'll talk more about how to effectively design solutions to problems in a future lesson. Write the program. In order to write the program, we need two things. First, we need knowledge of the programming language. That's what these tutorials are for. Second, we need a text editor to write and save our written programs. The programs we write using C++ instructions are called source code, often shortened to just code. It's possible to write a program using any text editor you want. It's something as simple as Windows Notepad or Unix's V or Pico. A program type. By the way, I'm a Nano guy, or either Vim. either Nano or Vim. Not really much of a V guy. Just want to throw that out there if anybody knows what that is. I would say for coding, I'm definitely a Vim guy though. Probably want to use Nano for coding. So I'm just copy and pasting something. Anyways, program types into a basic text editor would look something like this. Hashtag include IOStream. Int main standard character output. Here is some text. Return 0. Okay. So this is basically just making a function called main with the return value as an integer. And within the block, which these little curly braces are the block, it has a standard, so it acts as in the standard library, the character out function. And so it basically prints out here is some text into the console. And then you have to always return something if it has, so its return type is integer, so we return 0. Anyways, however, we strongly urge you to use an editor that is designed for programming called a code editor. Don't worry if you don't have one yet. We'll cover how to install that code editor shortly. A typical editor designed for coding has a few features that make programming much easier, including line numbering. Line numbering is useful when the compiler gives an error. A typical compiler will state some error code / message line 64 without an editor that shows the line numbers. Finding line 64 can be a real hassle. Syntax highlighting and coloring. Syntax highlighting and coloring changes the color of various parts of your program to make it easier to identify the components of your program. So like, you see how this is colored right here because this is a function, so it's colored yellow. Strings are colored in green. Just things like that. An unambiguous fixed width font, often called a monospace font. Non-programming fonts often make it hard to distinguish between the number 0 and the letter O, or between the number 1 and the letter I, or lowercase l, sorry, and the letter I, uppercase I. A good programming font will ensure these symbols are visually differentiated in order to ensure one is an accent used in place of the other. All code editors should have this enabled by default, but a standard text editor might not. Using a fixed width font where all symbols have the same width makes it easier to properly format and align your code. Here's an example of C++ program with line numbering, syntax highlighting, and a fixed width font. Yeah, how sexy is that? So yeah, their strings are coded in red. That includes a red. Their functions are orange. Integers are blue. I'm pretty sure my integers are... Yeah, mine is mainly just green. Like different shades of green. Yeah. Note how much easier this is to understand than the non-highlighted version. The source code we showed in this tutorial will have both line numbering and syntax highlighting to make that code easier to follow. Tip: coding font and programming fonts both have neat tools that allow you to compare different coding fonts to see which one you like the best. For advancers, because source code is written in ASCII, using ASCII characters, programmers use a certain amount of ASCII art to represent mathematical concepts. For example, not equal to is not part of the ASCII character set, so programming languages typically use not equal to represent mathematical inequality instead. Some programming fonts, such as Firacode, use ligatures to combine such art back into a single character. For example, instead of displaying not equal to, Firacode will display not equal to using the same width as the 2-character version. Some people find this easier to read, others prefer sticking with the more literal interpretation of the underlying characters. Yeah, we're not going to be doing this. I'm going to stick to the more literal interpretation of the underlying characters, because if you're going to be, if you want somebody else to read your code and they don't use that, they're going to have no idea what's going on, right? So yeah, we'll have to stick to the standard, yeah. Many simple C++ programs only have one source code file, but complex C++ programs can have hundreds or even thousands of source code files. Each source code file in a program will need to be saved to disk, which means each source code file needs a file name. C++ does not have any requirements for naming files. However, the de facto standards name the first primary source file created for a program main.cpp. The file name main makes it easy to determine which is the primary source code file, and the .cpp extension indicates that the file is a C++ source code file. You may occasionally see the first primary source code file named after the name of the program instead, for example, calculator.cpp, poker.cpp. I also occasionally see the extensions used .cc, .cxx. Name the first primary source code file in each program main.cpp. This makes it easy to determine which source code file is the primary one. Once you've written your program, the next step is to convert the source code into something that can be run, and then see whether it works. We'll discuss those in steps 4 to 7. Okay, I'm gonna call it here for this video because that was fucking long. Bunch of fucking reading.